and again, one more time reminder, your exam is not next week, but a week after next week, Tuesday, covering chapter 2 and 3.1. And 2 days we will work on 3.1 starting today. This was for the recording purpose. So 3.1. This one is good. And let's see how it is in here. Okay. So in 3.1, we're going to work on some applications. So let me open the book. Linear models. Linear models. So we're going to apply our knowledge. So we'll start with, there are so many different applications we can use differential equations on. We'll concentrate on three kinds. The first kind of application we will work will be population first application. Population growth or decay. That's the first topic. And this is what we'll do today. So let's pretend there is a population, could be human population, some bacteria, something that is growing or decaying. So let's say a population changing, which changing means growing or decreasing in number, proportional to the amount or to the number of population. I should have said a little better. I meant to say the rate of change. I meant to say the rate of change of population is proportional to the number of population. So let's see what that means. Let's say P is the population number. It depends on time T. At the number of things or number of people or number of bacteria, number of whatever in your population. T is the time. So if that's the case, if the P is your number of population, what does that mean? The rate of change of that population P. What is that? Derivative. Rate of change is derivative. So it's going to be what? dP dt. That's how population is changing. Just think it's proportional to what? To the P. So dP dt, the change of population, is proportional to P, means equals some number times P. So derivative of P, the change of P, is some number times P. That's what proportional means, right? That's what proportional means. So this is, we have this kind of thing. And we're going to have initial condition, population at the beginning of time is something, some number. There's an initial population. So this becomes a what? This becomes a differential equation, initial value problem. So we'll try to solve that. By the way, is this a linear? Well, instead of y, what do we have? P. Instead of x, what do we have? Well, we should look here. T. What is K? K is a constant. K is a number. K is the constant. Let's just say constant. Some number. But this should indicate, right? This is your y, this is your x, right? Does that make sense? So this is what kind of equation is that? What kind of differential equation is that?
First one?
First order, great, what else? How else we categorize? By order and by what else? Linear or not? It is, right? But it is the same as like dy dx equals some number times y, right? That's what I have basically. It's linear first order. Does that make sense? Instead of 5, I have what? Another number, k. But we know how to solve that. Let's solve that. So, well, there's two ways to solve it. Because could be solved as linear, but it's also possible to separate because there is no even addition, right? Separate p and a t. So it's our choice which one to practice, either linear, integrating factor, or separation. What do you want to practice? You let me know. Because it seems like it's both of those guys. What do you want to practice? Okay, let's go with linear. If I want to solve as a linear, what do I do? The linear would be like something that I can write what? I can also separate, by the way, right? We'll maybe try to write how I separate, but linear means what? I can write this dy dx plus some function of x, right? So now the same p as that, times what? Y equals some function of x. Can I write it that way? Well, instead of y, I have p, right? Instead of x, I have a t, so how would I write that? dp dt, is that one?
Plus k times.
But this is the question I have, right? Can I write it in that form if y is the p? Online students are allowed to talk? I cannot. Why?
Well, I think there's not enough. Like,
Can I subtract the kp? Would it be like this? Right? Well, this is like my y, right? This is this guy. My p of x is what? That. My f of x is 0. Why not 0? It's even easier, right? Does that make sense?
yeah, I don't think it could be zero.
Yeah, of course. What is f of x is 0. Y is 0. Or not y. This is different y. Y is something else, right? Yeah. So if you go that way, then our integrate, by the way, what if I wanted to separate? What would I do? How would I what if I will do this, but what if I wanted to separate to solve as a separable, what would I do? P is on one side, P is on the other, right? How would I do that? If I wanted to do it that way. How would I separate P and P?
You would just divide both sides by p and divide both sides by dt.
Correct. You could divide the P, so it goes with the dP, right? So that's gonna, now you could, the K, you can leave it there or you can take it there, it doesn't matter, it's a number, right? It's, okay. And then that will be the dP, and then you can multiply the dt, so it goes to the, because there's no other t but dt, right? So we get that, right? That will be separated. T's are there, p's are there. Does that make sense? Or we can try also this, but whatever you want to practice, we can just do that one. Are you okay with that? So let's go with this one. Maybe that's a little easier, I guess. Is it? Let's just see if you remember how to do that. If I want to go with that one, the what? It's a linear equation. My mu of x is what?
E to the integral of negative k.
Correct. E to the p of x. The confusion is this p is not the same as that p. This is like your y. So it's gonna be integral of what? Oh, maybe I should say, what is my p of x?
Negative k.
Negative k. So that's gonna be e to the what? Integral of negative k what? Dx. But that will be what? K is a number, right? So what will be the integral of that number? No, so we are solving that. So P mu of X equals e to the, what is it? No, what is the integral of a number?
B negative kx.
Right? Is that right? Negative Kx. So is that what we got? Cool. So then we multiply by that both sides. Is that what we do? Do you remember that? That should be in your exam. So we take that guy and multiply both sides of what? By this guy, right? That side. But that side is easy. That's going to be a 0, right? So on that side, it's going to be a 0. On that side, we have this guy. Oh, it's this. That guy times whatever it was there. dp dt minus kp. But this always has to be changed with a derivative ddx, in this case ddt of who? Mu of xy, but instead of mu of x, we have what? And instead of y, we have what? And the other side becomes 0. Then we will what? Take a derivative, and that's already a derivative. The opposite, the integral, right? This should be thrown away. Ah, I'm so wrong. Something is wrong in my notation. Can you figure out? Yeah, we don't have an x. Instead of x, we have a what? T. So even right here, mu of x in reality should be what? Mu of t. All the x's should be a what? A t. Are you okay with that? So I should have said here what? T. I should have said here T, T, T. So T, 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 I don't have X. And the T, let me just, this was the kind of formula. There's gonna be D what? D, T. T, dt, dt. Integral and derivative cancel, we get what? We get what?
We just get e to the negative kp.
Nice. E, right? And that, what is the integral of 0?
What do we need to?
Huh? Okay, how do I try? T or not? I have to take the derivative of that and get that, right? Is derivative of t 0 or 1?
Oh, it's gonna be 1.
So t is not gonna work, right? Derivative of that should be that, right? 0 will work, but it doesn't. How about like some number? What is the derivative of a number? It's 0. Does that make sense? Cool. Or 0 plus c if you want. Okay with that. Cool. So, but yeah, okay. So how do I find the c? We had the initial what? Condition. We know when the time p of 0 is some number that we call p0. That means when time was 0, population was this number. So we'll plug them in there, right? So I plug in t0, that's gonna be e to the 0, I think. And my p is what? P0. But e to the 0 is what? 1, so c becomes what? P0. So right, the initial number of population becomes the c. So let's write that down. So we got this guy right there. Well, e to the negative kt times P equals P0. I should write some kind of thing. Now, we saw, what are we solving this for? We usually solve for Y, right? In this case, we solve for who? What was the instead of Y? P. So how do I solve it for P? P0 is a number. That's the Y, that's the P. So how,
Both sides by E to the.
yeah. Cool. So P of T will be equal to what? How else I can write that?
Zero to E, eighty.
Like that. So this is the solution of that problem. So if the population rate of change is proportional to the population itself, population will be this. Number of the population will be initial population times e to the kt. Now we got that. Now we'll use that for some problems, complications. Now, it will be maybe a little easier to solve by separation, but I wanted to review this integrating factor. Okay, let's do some more problems from these exercises for population growth. So 3.1 exercises. Let's look at number. Let's start with number. I can use that. Close that thing. Now, I know this problem. Okay, cool. So maybe I can, yeah, I can. So let's look at number 2. Oh, so yeah, number 2 actually related to 1. If I want to do 2, I have to do 1. Hold on. It's a suppose it's known that the population in problem 1 is 10,000 over 3 years. Whatever. Population, I'm reading 1. The population of the community is known to increase at a rate. If initial project, okay, let's do 1 and 2 together. Maybe 1. Okay, what's that? The population, because 2 refers to 1. The population of a community is known to increase at a rate proportional to the number of people present time. So a population is growing proportional, growing at a rate proportional to the number of population. Anytime you have that statement, if you call population number P, this thing changes to this. Population equals the change of population equals some number times the population itself. And that's something we already solved. So this statement, this sentence means that. Okay, so let's see. If an initial population has doubled in 5 years, doubled in 5 years, how long will it take to triple? How long will it take to triple? Now we could start from here and solve this. But we already solved that. So when we solve that, what we got? Population number equals what? Initial population times e to the kg. So this is how we got that. We solved that. Does that make sense? Okay. Now what? So we have what? Initial population doubled in 5 years. What does that mean? In terms of symbols.
So T equals 5.
So it says if t equals 5, what? Initial population doubled.
I think 2PO or double 2PO.
So the population number, let me first write it differently. So it means population number after 5 years equals double of initial. Is that right? Do you agree with that? So that means if t is 5, population number is double of the initial. That's what it means, right? Well, let's plug in there. So how would I get if I plug in?
2PO.
Yeah, 2 initial population equals initial population e to the what?
K5.
Yeah. And that will help us to solve and find a what? Okay. How do I do that?
Divide by PO.
Divide by?
Initial population.
Oh yeah, that's what I just did. Sorry. Divide the initial population, cancel it. Okay, that's good. How about after that? The P0 is gone. We divide it. Then what? How do I get a K?
Natural log.
Natural log. ln of 2 equals ln of these, then what?
The L and the E cancel out, right? And the 5.
Yeah. So this is some number in your calculator, but this is exact, or you can approximate. We got a K. Now with that K, our population formula will become P0 e to the K, this guy, T. This number that's our formula. So we got a K. So how do we answer this question? How long will it take the population from initial stage to triple? From the beginning. Yeah, right. We have to plug in something.
You would plug in 3P initial.
Correct. So this says how long will it take, which means find the T when population becomes triple of what it was. Yes?
Yeah.
So that's gonna be, this is the population number equals this. And we are asked to find the time, then we'll what? By the way, I want to emphasize, we are not, the only time we did differential geometry, solve differential equation today was when I derived this formula. Now we're not doing differential equations, we're doing algebra. Does that make sense? Okay, cool. So how do I solve that?
Initial population.
Correct. Divide by the initial population. Then what?
The natural log of both sides.
Take the natural log on both sides.
divide by, natural log of 2 or 5 on both sides.
So to move that to the other side, you can flip that, right?
So multiply
Multiply by the reciprocal of that. So then T will be ln of 3 times 5 over ln of 2. This is some number in your calculator. Questions there? Okay, let's look at another problem. Okay, let's look at another problem. See, maybe we look at number 3. Oh, number 4. Let's look at number 4. The population of bacteria in a culture grows at the rate proportional to the number of bacteria present in type T. All those problems gonna have this. They're gonna have the population number grows at a rate proportional to the population itself. That means for all of them, we are gonna have that differential equation whose solution is going to be that. So then we have the following. After 3 hours, this is number 4. After 3 hours, so basically we have this dB dt equals K times P. This means the rate of change is proportional to population. We have after 3 hours. After 3 hours, it is observed that 400 bacteria are present. So 400 bacteria are present. And then we have, after 10 hours, 2,000 bacteria are present. Oh, wait. What was the initial population of the bacteria? Which means that times zero. Okay. So again, we have that formula. And if we have that formula, we already solved that. We know the solution of that has to be this. Okay. So we solve that. Okay, then what? So let's see, what can we do, let's say, with this first sentence? And I plug in a first sentence there. What do I write?
Right, 400 is equal to P, 0, e to the. Isn't it just 3T? Or just 3? 3K?
The 3 is your what? T. So what do I write? 3. Okay. The T is 3, right? Can we plug in this other sentence into the formula? What would that sentence give us?
Equals E times E to the 10K.
So now we have 2 equations, right? With how many unknowns?
2.
2 unknowns. So something we may be able to solve because we have 2 of those. So how we can try to solve that? Well, the idea is to find a what? P0, but we should be able to find both K and P0 because we have 2 equations. So any ideas what to do? I think there's more than one way to solve this system. Now we're doing algebra, by the way. Yeah, any ideas?
In isolate one of the variables.
Sure, let's isolate one of the variables, like which one you want. Okay, so how do I get the P0 from the first equation, if that's what you're saying, right? So you're saying that's a P0 from that one, what would the P0 from there?
We will, 400 divided by 8 to decay.
Okay. That one.
We plug it into the second.
So you want to substitute that in here? Okay, if you substitute that in there, what do we get?
400 into decay times e to the decay.
Okay, then what? So you need a substitution, then what?
We
But this-
subtract the e powers.
Simplify e to the 10k over e to the 3k, but 10k minus 3k, which will be what? 7k, so he says this will become this. Now it says only k, so maybe able to find it by doing what? Divide by 400. E to the 7k, yes, we can cancel those zeros and those zeros, and 20 over 4 is what? 5, then what?
You take the natural log plus
So 7k will be what?
5 divided by 6.
So we got the k, so how do we get the what we are asked for to find the P0? Yeah, we already have that, right, for P0. But you're right, we could have done that. So P0 equals 400, what? Over e to the 3k, that's gonna be 400 over e to the 3 times that, right? By the way, I'm done, because this is some number. Calculator can calculate that, this is some number, and that's you want it to have. See if we can do another problem. So that was, half-life. Let's talk about half-life. So let's say we have a certain number of something, certain number of bacteria, or certain number of some population. So certain grams of some chemical that is decaying. So let's say, I don't know, we have 400 grams and it's decaying or whatever. It becomes less and less and less. What would that mean to half-life of that thing? Let's say if I have some chemical that is decaying, so I'm getting less and less and less. Anybody knows what I mean when I say half-life of that thing, let's say, is 1 year? Who knows that? Half.
In 1 year, half of the mass of the initial.
Correct. That means in 1 year, half is gone. Or in 1 year, only half is left. And then another year, whatever was left, half of that is gone. Another year, half of that is gone. Every year, half is gone. That's what half-life. It's a half-life is 2 years. After 2 years, half is gone. Or only half is left. Cool. So let's see if we can do a problem using that concept. So 5 is about half-life. The 6 uses that idea, but not doesn't say half-life. Oh, yeah, but let's do number 6 with the half-life because the 7 preferred. Initially, 100 milligrams of a radioactive substance was present, number 6. Initially, I forgot what I just said. 100 milligrams, 100 milligrams. So 100 milligram of a radioactive substance. 100 milligram of some, let's say, substance was present. Determine, oh yeah. Yes, determine the half, no, but hold on, let's just write the whole thing. After 6 hours, the mass has decreased by 3%. After 6 hours, the mass has decreased I think I said 3%. Did I say 3?
You said 6.
No, I can't remember. I'm so bad at memory. I really am. No, 6 hours, the mass has decreased by 3%. By 3%. This is part A and part B. Part A says, find amount remaining after 24 hours. Find amount remaining after 24 hours. After 4 hours, 24 hours. After 24 hours, after 1 day. Okay, and there's part B about the half-life. So how do we, well, we know, but I forgot to write important thing. Important thing was the amount of this thing is decreasing proportional to whatever amount was there. If the rate of change is proportional to the amount that was there at the beginning, that means this formula applies. I omitted that. So rate of change is proportional to the amount of the thing at the beginning. So this formula applies. Then we have that formula, that solution. Okay. So that means we can write. That means we can write. That means we can write the population amount is initial population into decay T. And then how can we try to use the information given? Well, first of all, they give us this. How can I translate that to much? That sentence, what kind of thing does it say? How can I plug in there or translate? After 6 hours.
So it'd be T equals 6.
I just realized I'm seeing S here. That was mass. SS. I apologize. Yeah, please go ahead.
We could, well, for the 6 hours, that would be T equals 6, and then decreased by 3%, I think would be 3 over 100 for the value of decreased.
Great. So it was initially, after 3 hours, so the initial amount decreased by 3, right? Does that make sense? There's two ways to think of that. He's right. Initially, it was P0, right? Is that right? If the P0, that was 100%. Now, what does it mean? 3% is decreased. He was so right. 97% is left, right? So that means that, so that this guy will be what? 97% of what was there. This is what? 97% of that. Am I making sense? 3% is gone, 97% is left. But that's not the only way to think of that, but that's one way to think of it. So that's the same to say as P after 3 hours will have to become 97% of that. So now we can plug that into the what? Into the what? Into the equation, and what do we get?
0.7 initial population.
0.97 P0 population number is when T is 3, right? So plugging the T is what? 3. And that will help us to find a what? A K, right? Mhm. So that will be our what? Okay. So we can rewrite the equation with that K constant. Yeah. So equation will change to P of T equals P0 e to the decay times. Now, what if we want to know the amount after 24 hours? What will the
Or you can take this, yeah.
plugging what?
Be relaxed. You know.
Income is just letter. So plugging what?
The 2415.
Yeah. No. Oh, well, yeah. What I forgot to say, I forgot to say is what? We have the initial what? Population or initial number is what? 100, right? P0, I forgot to say, I apologize. P0 was given 100, so otherwise you couldn't do that, right? Does that make sense? Now, I could have also plugged in here. I didn't realize I had that, but here it didn't play a role. So instead of what I could have done here at the beginning, if I saw, I didn't realize. If I realized that initial population is given, the number of the population, I could make your life a little easier. I can say what? If initially was that, if 3% is gone, then only 97 is left, right? So I could have replaced what I could have done previously. I didn't notice that, by the way. I could have say T equals 3, P equals just 97. Do you understand that? Then I could write what? The what? 97, this is the P, right? Instead of writing this. I thought I don't have the P0, but I did. Equals what? P0, that, right? But I would get the same thing. Does that make sense? I thought I don't have the initial condition, initial number, but I did. But again, that will give me the same thing as we got. Does that make sense? As to get 0.97, just like there. So it didn't change thing, but I just didn't notice that. The reason I notice it now, because I realized I cannot do this problem unless if I have the P0. That's why I went back and read it again. Does that make sense? Is that okay what I'm saying? The 97% of 100. Cool. So if we continue now, we have the P0. I think that's what he was saying. He was saying, I think he was saying 97 over 100 or something like that. I forgot, yeah. And I didn't realize that. But anyway, nothing is wrong. So that's gonna be what? 100 times what? Is that right? 0.97 over 3, and then T is what? 24, right? T is 24. It is almost there, but 24 and 3 will become an 8. So can rewrite this as that? And this is some number in your calculator. I cancel 24 and 3. Everybody okay with that? Okay. This is a part B about half-life. Let's see if we can look at that. Mhm. Okay, part B is problem 7. It says, go back to that problem and find the half-life. So I just write this part B because it's about the same problem. So find the half-life of this substance. Find the half. Maybe I need to do like that. Half-life, I don't know. Maybe I need like that. Half-life of that substance. Mhm. So half-life means what? So many ideas. Half-life means we have to find a what? Time, right? So we have to find the time. What kind of time? When P0 becomes what? Well, half is gone, right? Or half is left. Half find the T when amount is what? Half of that, right? When half is left. Now we'll just plug in rho. So we'll plug it into our equation. This is the equation that we have with the K we already found, right? We'll just plug in here. So the amount is left, right? Is half of P0. Oh, I'm doing the same mistake because P0 is not important here, but we do have the P0. Now, you always can find the half-life even without having P0. But in this case, I just realized we do have the P0, right? The P0 was 100. Does that make sense? So maybe I can just do a little better job here. What I'm saying, if we didn't know the P0, I can cancel. So it's not gonna play a role. Whether initially was 100 gram or million gram, it's not gonna play a role. We are gonna find the same half-life. Because why? Because the P0 is gonna cancel. Doesn't matter I had million gram of that thing or 5 gram, this is not gonna play a role. Let's see that's gonna go. In the half-life, it doesn't matter, right? But let's just write, so this becomes a what? 100 over 2, which is what? 50. Does that make sense? So we have 50 equals, and then here, and again, P0 is a what? 100, because we had it. E to the ln of 0.97 over 3 times T that we want to find. Then what do we do? Divide both sides by 100. No, I don't know, to write it as a fraction or to write it as a decimal. Fraction, what happened? Then what? Check ln. Let's write 0.5. Because we only have a decimal here anyway. 0.5. Now if you have questions, please let me know. Do you know what I've done? This P0 was 100. I place it. And this is what? Half of the 100, right? 50. Are you okay?
Yeah.
If you have a question, that's why I'm. If you have a question, you should ask. You have time.
The 3 was.
Oh, I don't know. There's 3, oh, but there's the 3K here. You see, what is that? I don't know what the 3 from.
We got it.
Professor, I think the T should be 6.
Oh, then we have to go back and look. I have no idea. Why is it 3? What is a 3
Yeah,
from?
yeah, it's after 6 hours.
Then why did I write 3? Oh.
I think because it was decreasing by 33%. I mean, 3%.
How come nobody said it before? Just 3? It's wrong. Because the time was what? 6 hours, not 3 hours. So that should have been 6. Now, I don't want to redo this whole thing. Would you let me if I do something wrong and change this to 3 hours? Is that okay? Are you okay with that? Yes or no?
Yeah, I've been writing
Yes.
Yeah, so I apologize. This is the T, right? K times T. I replace it by the 3 instead of replacing by what? 6, that was a 6. So now this 3 is the hour. So I'm gonna keep everything and just change this. The problem, I apologize for that. How come you just saw it? Okay.
Because, what I've been.
Or did you see it before, you just didn't want to say it?
No, it's, because I've been following the process, but now I'm
Oh.
actually looking, like, copying down one for one.
So I apologize, that should have been the hours, which I copied wrong. Okay. Yeah, so continuing this problem with the 3 hours instead of 6 hours. So then we have this, then what is left is what? Take ln on what? Both sides. So ln of 0.5 equals ln of e to some number times t, and that will give us ln of 0.5 equals to that. And to get the t, we'll multiply by the reciprocal of this on that side. That will be the time t. Three over that, so that will be some number in your calculator for the t. And I think it was hours. So after that many hours, half of the thing will be gone. If that was 6 hours initially. Questions about that? Now, what was interesting thing to notice again, for the half to find a half-life, it doesn't matter what the initial was, because that's gonna cancel anyway. Half of P0 is gonna be left, we just can't cancel. Anyway, so let's see what we are doing. I think today we're just gonna look at this one application and then we're gonna do the rest. But because we have more, I don't think we will be able to do all of that. I wanted to do 3 kinds, but let me just see if I can get one more of the growth and decay. So, okay. Yeah, I guess, okay, this dating could be also considered the same thing. Let's see, oh, and then they start the Newton's law. Let's see, I think we did, I guess we can move on to what? We can, let's just reduce, let me just go back for a moment to 3.1 here. Okay, that's fine, it's fine, it's fine, I don't want that. I guess we can start looking at the other application, but we continue it next time. Okay, so the next application will be Newton's law for cooling or warming. We'll continue it next time, but we'll just solve maybe that in general. So let's just explain it. So next application, second application. Newton's law of cooling. Or should I say heating or warming? What is the opposite of cooling? Warming, heating? Warming. Okay. So let's say we have the following situation. So we have some environment. This could be a container, could be a room, some box. So this box or this room or this environment has some temperature. So some temperature this guy has. And then we bring from outside something, some object, and we place that object in here. So the temperature of this box, I'm gonna call Tm. That's the temperature of this environment, of this box, of this room. And then we put some object in here. This object that I place in this environment has in some initial temperature. So this guy has some initial temperature, let's say T0. This is the kind of the room temperature. And then depending on this temperature of this room is, temperature of this thing can either what? Cool down or what? Warm. If it's a refrigerator, maybe it will start, and will start what? Cooling down. If this is like a high temperature, this is gonna get warmer, right? Like, does that make sense? So what we are gonna do, well, the T will be the temperature of this object that is changing. So the Newton's law says the rate of change of temperature of this guy, the rate of change of temperature of that guy, equals some K constant times T, the temperature itself, minus this temperature of that room. This is Newton's law. The way the temperature of this thing will change, the rate of change of the temperature is some constant times the temperature itself of that thing minus the temperature of this new environment. And then, of course, we have T temperature at the beginning was, or temperature at the time 0, it's like some T0. So it's initial value problem. So this has some initial temperature, and then it's changing according to that law. Okay. So this Tm is called ambient temperature, that room temperature. Environment temperature or something. So let's see. No, before doing the problem, so let's do some differential equations and solve this. There could be two situations. In one case, the easiest case, the temperature of this room will be constant. Like you set your refrigerator temperature to some constant thing. It's always the same. But the second situation may be a little harder, then this temperature also can change. The temperature of this refrigerator can change, not stay constant. But first we'll solve it when this Tm, the K is a constant. In the first case, this Tm, temperature of this room, is also gonna be a number, constant. That's a constant, that's a constant. Then I will make it a little hard and I will say, oh, let that not be constant. So let's say we have a number here, we have a number here, we have an initial value problem. Instead of y, what do we have? For this differential equation, we always solve for y, capital T, and instead of x, we have what? Time t, small t. So we're gonna solve this. So well, for now, we know only two kinds of equation to solve, unfortunately. One of them is what? If you can what? Separate, and the other one, if it's a what? Linear. So I think this one could be treated both of them. So it's like which one you want to practice. I think I'll go with practicing linear again. Maybe separable is a little easier. So how do I change this to a linear equation? So how do I rewrite it as dy dx plus some function, something like that, and the x is a t, y is a capital T. Yeah, yes.
Distribute the K?
Mhm. Right? Okay. Oh, this is just a number, right? So then what?
Subtract KT.
Subtract QT. And so what is your P of X? Or maybe P of, yeah, maybe P of T. That guy.
Okay.
And K. And what is your mu of X, mu of T, e to the integral of negative K T dt, sorry, dt, and that becomes what? E to the negative K. And then we multiply both sides of our equation by that. So we have e to the negative kt times dt over dt minus kt equals e to the negative kt times the other side. And then this will become derivative of who?
UT and 1.
Right. So that's e to the negative kt times what? T? And that one, this is a number. So it's a sum number times that. So what do we do next? Integrate, right? On the left side, of course, we will get what? E to the negative kt times t. But if it's a number, this number can go outside of integral, right? And what is the integral of e to the number times t? Like what is the integral of e to the ax dx?
Then it e to the ax divided by a.
Right? By u sub, right? If you call u equals ax, you get that. So with that same thing, what would you get here? 1 over what? Negative k, right? E to the negative kt, and plus some c. Negative k will go what? Away? Cancel? So we have what we have. But let's solve this for t. So how do I solve this for t? Temperature t. I'm writing it down. How do I solve this for t? Divide by.
E to the negative KT.
Well, we got the temperature T. Let me do this. So that's gonna be what? Tm plus C times that, right? Is that right? Can we find a C? Temperature at the beginning was T0. Plug that in, right? So this means plug in small t 0, big T is t naught, t0. So you get t0 equals tm, and that's a 0. So that's gonna be 1. It's gonna be plus c. Yes. E to the 0. So then c will be what? T0 minus tm. So I'll replace it there. So the what temperature at the time t will be the room temperature plus T0 initial temperature minus the room temperature. Now next time we'll start by, you have a homework question I will answer, and then we'll continue from Newton's law, application of Newton's law. Any questions, comments, remarks from online and or from in class? I want to remind online and not online students that your exam is not next week, but the week after next week, Tuesday, and it includes up to this section, but we have 2 more applications, more problems to cover. March 10. Okay, I'll see you in next week. Please work on the homework, and if you have questions, bring them. I'm going very slow, by the way. Okay. Bye, everyone.
Have a good night, Professor.
Thank
you.